Hello everyone, welcome to my YouTube channel. So today we are going to learn about artificial intelligence and how it evolved during its history and came to recent existence. So imagine waking up in one morning and discovering that every computer in the world has suddenly become intelligent. Your phone understands every question you ask. Your car drives itself safely through crowded streets. Your doctor uses an AI system that can detect diseases years before symptoms appear. Your teacher is available 24 hours a day, never gets tired, and can explain even the most difficult concept in 100 different ways until you understand it. Movies are written by machines, music is composed by algorithms, scientific discoveries that once took decades now happen in months, businesses run faster, hospitals become smarter, and robots begin working alongside humans in factories, offices, farms, and even homes. Now ask yourself one question: would this be the greatest achievement in human history, or the beginning of the greatest transformation civilization has ever experienced? Because whether we realize it or not, this transformation has already begun. Welcome to the age of artificial intelligence. This isn't just another technological revolution like the invention of smartphones or social media. This is something much larger. Electricity changed how humans used energy. The internet changed how humans shared information. Artificial intelligence is changing how humans create intelligence itself, and that single idea has the power to reshape every industry, every profession, every economy, and perhaps even what it means to be human. Today, AI writes books, creates paintings, composes music, designs buildings, discovers medicines, translates languages, drives cars, predicts weather, identifies cancer, generates computer code, and answers millions of questions every single second. But here's something even more fascinating. Just a few years ago, many of these achievements seemed impossible. Scientists believe that creating machines capable of understanding human language would require decades of research. Yet today, millions of people casually talk with AI systems every day as if they were chatting with another person. How did this happen? How did humanity go from room sized computers that could barely perform basic calculations to machines capable of writing poetry, solving mathematics, creating artwork, and assisting scientists in discovering new knowledge? To answer that question, we must travel backward, not just years but centuries. Long before computers existed, long before electricity illuminated our cities, long before the first machine was ever built, humans dreamed about creating artificial life. Ancient Greek mythology described mechanical servants made of bronze that obeyed commands without question. Chinese legends spoke of artificial humans crafted by inventors. Medieval engineers built astonishing mechanical clocks filled with moving figures that amazed everyone who saw them. People have always wondered whether intelligence could be created instead of born. For thousands of years, that question remained philosophy. And then mathematics entered the history. Even great technological revolution begins with an idea that seems impossible. In the 17th century, philosopher Rene Descartes imagined the universe operating like a giant machine governed by logical rules. Later, mathematicians discovered something extraordinary. Any calculation, no matter how complicated, could be broken into smaller mathematical steps. That discovery planted a seed. If thinking could somehow be represented mathematically, perhaps thinking itself could eventually be performed by machines. At that time, this sounded absurd. After all, humans possess emotions, imagination, memories, creativity, and consciousness. How could gears and metal possibly imitate something as mysterious as the human mind? No one had the answer. But then came one of the history's greatest thinkers, Alan Turing. During World War II, Turing worked on one of the most secret projects in history. German military communications were encrypted using an incredibly sophisticated machine called Enigma. Millions of lives depended on breaking its code. Most experts believed it was impossible. Turing disagreed. Instead of trying to solve every message manually, he designed machines capable of testing enormous numbers of possibilities automatically. Those machines helped decode enemy communications, shortened the war, and saved countless lives. But after the war, Turing asked an even bigger question. If machines could solve problems, could they also think? In 1950, he published a revolutionary paper introducing what later became known as Turing test. The idea was beautifully simple. Suppose you communicate through text with two hidden participants. One is human, the other is machine. If you cannot reliably determine which one is the machine, has the machine demonstrated intelligence? Notice something remarkable. Turing didn't try to define intelligence. Instead, he judged intelligence through behavior. If something behaves intelligently, maybe that is enough. This question still echoes through laboratories and universities around the world. What exactly is intelligence? Is intelligence memory? Computers remember far more information than humans ever could. Is intelligence speed? Modern processors perform trillions of calculations every second. Is intelligence knowledge? The internet contains vastly more information than any individual could memorize. Clearly, intelligence must be something deeper. Perhaps intelligence is the ability to learn, or adapt, or reason, or solve unfamiliar problems, or create something entirely new. Scientists could continue debating this question even today. Ironically, before we could build intelligent machines, we first had to understand ourselves. The year was 1956. A small group of researchers gathered at Dartmouth College in the United States. The meeting wasn't particularly large. No television cameras, no global media, no billion-dollar companies. Just scientists discussing an extraordinary dream. They believed that every aspect of intelligence, learning, reasoning, language, problem solving, could eventually be described so precisely that machines could simulate it. During the conference, one phrase appeared for the first time: artificial intelligence. The participants were incredibly optimistic. Some predicted machines with human level intelligence within 20 years. History had different plans. Early AI systems could solve puzzles, play simple games, and prove mathematical theorems. These achievements seemed miraculous, Newspapers announced that electronic trains were arriving. Governments invested heavily. Universities created new research laboratories. Excitement exploded. Then reality arrived. Real world intelligence turned out to be unimaginably difficult. A child effortlessly recognizes their mother's face. A toddler understands that a glass will fall if pushed from a table. Humans learn language naturally. We recognize sarcasm, understand emotions, infer intentions, navigate unfamiliar environments, identify objects from unusual angles. These abilities appear effortless because our brains evolved over millions of years. Programming them manually became a nightmare. Researchers discovered that intelligence wasn't one problem, it was thousands of interconnected problems. Progress slowed dramatically. Funding disappeared. Many researchers abandoned AI entirely. This period became known as the first AI winter. The dream seemed frozen. Yet somewhere quietly another revolution was beginning. Instead of teaching computers every rule, what if computers could discover rules themselves? Imagine teaching a child what a dog looks like. You could describe every possible detail: four legs, fur, tail, ears, eyes, different breeds, different sizes, different colors, or you could simply show thousands of pictures. Eventually, the child recognizes dogs naturally. No one explains every mathematical rule. Learning happens through experience. This simple observation changed everything. Instead of programming intelligence, scientists began training intelligence. The computer wasn't told exactly what to do, it learned by examining examples. The new idea became known as machine learning. At first, the results were modest. Computers classified handwritten numbers, recognized simple speech, detected spam emails, recommended products, nothing particularly dramatic. But hidden beneath these small achievements was an extraordinary realization. Every additional piece of data made the system better. Even improvement in computing power made learning faster. Every new algorithm unlocked capabilities nobody expected. Then something remarkable happened. The internet arrived. Suddenly, humanity was generating information on a scale never been seen before. Every search, photograph, email, article, video, every social media post, online purchase, scientific paper, together they formed one of the largest collections of human knowledge ever created. For machine learning, data was food, and suddenly there was an unlimited buffet. At almost exactly the same time, another expected hero entered the story: video games. Yes, video games. Gamers demanded increasingly realistic graphics. To satisfy them, companies designed specialized processors capable of performing millions of mathematical operations simultaneously. These processors became known as graphic processing units or GPUs. Researchers soon realized something incredible. The same hardware used to render explosions, racing games, and fantasy worlds could also train enormous neural networks thousands of times faster than traditional computers. The gaming industry accidentally accelerated the AI revolutions. No one planned it. Innovation rarely follows predictable paths. Around the same period, cloud computing emerged. Instead of purchasing expensive supercomputers, researchers rented computing power over the internet. Small startups suddenly gained access to resources previously available only to governments and giant corporations. Ideas spread faster, experiments became cheaper, progress accelerated. Then, in the early 2010s, the impossible began happening. Computers recognize faces more accurately than humans in certain situations. Speech recognition improved dramatically. Machine translation became genuinely useful. Image classification reached astonishing accuracy. For decades, AI had taken tiny steps. Now it started sprinting. Every few months, another breakthrough appeared. The world watched with curiosity. Most people still believed AI would remain something used only by scientists. Few realized that within a decade, AI would enter classrooms, offices, hospitals, homes, smartphones, and everyday conversations. Then came a moment that changed public perception forever. People stopped asking whether AI worked. Instead, they began asking whether AI would replace them. Artists wondered if machines could create art. Writers questioned whether algorithms could write stories. Programmers debate whether AI could generate software. Doctors explored AI assisted diagnosis. Teachers experimented with intelligent tutoring systems. Business leaders transformed entire companies. Students suddenly had personal tutors available 24 hours a day. For the first time in history, intelligence itself became scalable. Think about that sentence carefully. Throughout history, every human expert represented years of education and experience. If one teacher could educate 50 students, another classroom required another teacher. If one doctor treated 1000 patients, helping another 1000 required another doctor. Human expertise has always been limited by the number of experts available. Artificial intelligence changes that equation. One trained AI system can assist millions simultaneously. That possibility could redefine education, healthcare, engineering, science, agriculture, and nearly every profession imaginable. But with extraordinary opportunity comes equally extraordinary responsibility. What happens when AI makes mistakes? Who is responsible? Can machines become biased? Should AI make life changing decisions? Can artificial intelligence be trusted with military weapons? Could misinformation spread faster than truth? While automation eliminated jobs faster than new ones appear. These questions have no simple answers. Technology itself is neither good nor evil. Fire can cook food or destroy forests. Electricity powers hospitals or causes deadly accidents. The internet connects humanity or spreads misinformation. Artificial intelligence follows the same pattern. Its impact depends entirely on how humanity chooses to build and use it. And that is precisely why understanding AI has become one of the most important skills of the 21st century. You don't need to become an AI researcher. You don't need a PhD. But just as reading became essential after the invention of books, a computer and computer literacy became essential after digital revolution. AI literacy is becoming essential for everyone because the future won't simply belong to people who use AI, it will belong to people who understand it. In the next chapter of our journey, we are going to ask a question that sounds deceptively simple. What exactly is intelligence? Why does a newborn baby eventually learn language without reading a manual? Why does the human brain consume less electricity than a household light bulb while outperforming the world's most powerful supercomputers in many everyday tasks? And why have scientists spent decades trying to imitate one of the most extraordinary creations in the known universe, the human brain? That is where our story continues. Close your eyes for a moment and think about something that no scientist has ever fully explained, your own mind. Right now, without making any conscious effort, your brain is processing the sound of this voice, understanding every word, predicting the next sentence, remembering things you have learned in the past, connecting new ideas with old memories, filtering distractions, and perhaps even imagining scenes as you listen. You aren't calculating anything manually. You aren't solving equations. You aren't consciously searching billions of memories. It simply happens effortlessly. And yet, behind this effortless experience lies the most complex object ever discovered in the known universe, the human brain. For thousands of years, humanity has looked toward the stars searching for mysteries. We have built telescopes capable of seeing galaxies billions of light years away. We have landed robots on Mars. We have photographed black holes. We have mapped the human genome. But one mystery remains astonishingly close to us, the three pound organ resting inside every human skull. Scientists estimate that the human brain nearly contains nearly 86 billion neurons. Even one of those neurons forms thousands of connections with other neurons. Together, they create trillions of communication pathways that are constantly changing throughout your life. Imagine every person on earth connected to everyone else by thousands of invisible wires. Now, multiply that network many times over. Even then, that comparison falls short of the brain's incredible complexity. Every thought you have ever had, every memory you have ever created, face you have ever recognized, language you have ever spoken, dream you have ever experienced, and emotions you have ever felt exist because billions of tiny cells exchange microscopic electrical signals every second. No central commander exists. No master computer controls everything. There is no single neuron responsible for intelligence. Instead, intelligence emerges from billions of simple units working together. That idea became one of the greatest inspirations behind artificial intelligence. But before scientists could imitate intelligence, they first needed to answer an even deeper question: what exactly is intelligence? At first glance, the answer seems obvious. Many people believe intelligence simply means being good at mathematics. Others associate intelligence with memory. Some think it means speaking multiple languages. Others believe intelligence is creativity. But consider this: a calculator performs arithmetic far faster than any human alive. Does that make it intelligence? A hard drive remembers more information than any person ever could. Does that make it conscious? A chess computer defeats the world's greatest players. Does it truly understand chess? Clearly, intelligence cannot be reduced to one skill. Instead, intelligence appears to be a combination of many different abilities working together. The ability to learn from experience, to recognize patterns, to solve unfamiliar problems, to adapt when circumstances change. to predict future outcomes, to communicate, the ability to imagine possibilities that never existed before, and perhaps most importantly, the ability to continue learning throughout life. Think about a newborn baby. Unlike many animals, human babies know almost nothing when they enter the world. A baby cannot walk, speak, read, solve equations, recognize every object. Yet, within only a few years, that same child learns language, understands emotions, recognizes thousands of objects, develops friendships, solves puzzles, asks endless questions, and begins building an understanding of reality. No software update installs this knowledge. No instruction manual downloads into the brain overnight. Learning happens gradually, experience after experience, mistake after mistake, curiosity after curiosity. This remarkable ability to improve continuously fascinated early AI researchers. Instead of programming every possible behavior, could machines also learn from experience? That single question transformed computer science forever. To understand why, let's compare how traditional computers operate. Imagine asking someone to bake a cake. A traditional computer needs exact instructions: how much flour, sugar, eggs, temperature, and how long to bake. Miss one instruction, and the computer has no idea what to do. It follows rules perfectly, but only the rules it has been given. Now imagine asking an experienced chef to create a dessert using whatever ingredients happen to be available. The chef adapts, improvises, learns from experience, recognizes patterns, makes judgments, changes the recipe if necessary. Human intelligence is flexible, traditional programming is rigid. For decades, this difference seemed impossible to overcome. Computers excelled the following instructions. Humans excelled at creating them. The researchers began asking a revolutionary question: what if we stopped telling computers every rule and instead allowed them to discover rules by themselves? Imagine teaching someone to identify apples. You could spend hours describing every possible characteristic: red, green, yellow, round, sweet, different sizes, different varieties, or you could simply show thousands of pictures labeled apple. Eventually, the learner discovers the pattern independently. Without realizing it, this is exactly how humans learn throughout life. Children don't memorize millions of formal rules, they experience the world. Patterns emerge naturally. Scientists realized machines might learn the same way. This simple realization became the foundation of machine learning. But another challenge remained: how could computers imitate the brain itself? The first attempts were surprisingly simple. Researchers imagined artificial neurons. Unlike biological neurons made of living cells, artificial neurons are mathematical functions. Each neuron receives information, processes it, passes the result to other neurons. Individually, these artificial neurons are incredibly simple. In fact, one artificial neuron is almost useless. But connect millions of them together, something extraordinary begins to happen. Complex behavior emerges. This is remarkably simple, similar to the human brain. One neuron cannot compose music, cannot recognize faces, cannot solve equations, but billions working together create consciousness, imagination, intelligence. Artificial neuron networks borrowed this same philosophy. Simple parts, massive cooperation, unexpected intelligence. Imagine standing outside a football stadium after a championship match. One person walking out tells you almost nothing. 10 people reveal slightly more. Thousands of fans living together suddenly reveal the game's outcome, the excitement, the celebrations, and even which team won. Patterns emerge only when enough individual pieces work together. Neural networks operate similarly. One artificial neuron detects almost nothing. Millions working together identify faces, translate languages, generate images, and even write software. Of course, modern AI is still fundamentally different from the human brain. Your brain runs on roughly 10 watts of power. This less electricity that's less electricity than many household light bulbs. Yet it performs tasks that still challenge the world's fastest supercomputers. Recognizing a friend's face across a crowded street, understanding sarcasm, creating original stories, learning from only a few examples, making common sense decisions. Modern AI often requires enormous data centers consuming millions of watts of electricity to achieve similar capabilities. In some ways, humans remain astonishingly efficient. Evolution spent hundreds of millions of years optimizing the brain. Artificial intelligence has existed for only a few decades. Despite this, AI has advanced faster than almost anyone predicted. But here's where things become even more fascinating. Human intelligence isn't only about logic. Imagine watching a sunset. The colors inspire emotions. A familiar song brings back childhood memories. The smell of rain reminds you of home. A simple photograph can make you laugh or cry. Human experiences combine memory, emotion, imagination, culture, relationships, and personal history into something deeply meaningful. Can machines experience beauty? Algorithms feel sadness? Artificial intelligence truly understand love? Today, the answer appears to be no. Modern AI can describe emotions, it can recognize emotional language, it can generate convincing stories about happiness or grief. But generating descriptions is very different from experiencing emotions directly. Think of it this way, that a cookbook contains thousands of recipes. It knows exactly how chocolate cake should be prepared, but the cookbook has never tasted chocolate. Likewise, AI can describe the experience of climbing Mount Everest without even feeling cold. It can explain music without hearing it. It can write about friendship without having a friend. Understand patterns and experiencing reality are not necessarily the same thing. This distinction is one of the biggest philosophical questions in artificial intelligence. Some scientists believe consciousness could eventually emerge from sufficiently advanced systems. Others argue consciousness requires biological processes that machines may never possess. No one knows the answer, and perhaps that uncertainty makes the question even more fascinating. Now, let's explore another remarkable characteristic of human intelligence: curiosity. Children ask hundreds of questions every day. Why is the sun blue? Do birds fly? Do stars shine? Why can't fish breathe outside water? Every answer creates even more questions. Curiosity drives exploration. Exploration creates knowledge. Knowledge creates civilization. Most certain AI systems don't possess genuine curiosity. They respond when prompted. They solve problems when asked. They don't wake up wondering about the mysteries of the universe. Humans do, and that difference may be more important than we realize. History repeatedly shows that breakthroughs often begin with curiosity rather than necessity. Someone wondered whether humans could fly. Someone wondered whether invisible waves could carry voices across oceans. Someone wondered whether tiny electrical signals inside the brain created thoughts. Curiosity built civilization. Perhaps someday AI will assist that curiosity more powerfully than ever before. But the curiosity itself still belongs to us. As researchers continued studying intelligence, another surprising discovery emerged. The brain doesn't simply memorize information, it compresses reality. Imagine meeting 100 different dogs. You don't memorize every individual hair on every animal. Instead, your brain creates an abstract concept, dog. That concept allows you to recognize a breed you have never seen before. AI researchers realized abstraction is one of the intelligence's greatest superpowers. Learning isn't memorizing every example. Learning means discovering the hidden patterns connecting those examples. This insight would eventually revolutionize artificial intelligence. Instead of storing billions of isolated facts, neural networks began learning representations, compressed mathematical descriptions, capturing the essential structure of reality. Suddenly, AI systems became dramatically more capable. They weren't just remembering, they were generalizing. And generalization is one of the defining characteristics of intelligence. By now, scientists had assembled many important pieces of the puzzle: learning, pattern recognition, abstraction, prediction, adaptation, neural networks, massive datasets, powerful computers. But one enormous challenge remained: how could machines understand human language? Language is unlike mathematics. Words change meaning depending on context. Consider the sentence, I saw her duck. Did she lower her head, or did she own a bird? Humans resolve this ambiguity almost instantly using context. For computers, language became one of the greatest challenges ever attempted. For decades, progress was slow. Researchers created grammar rules, dictionaries, language databases, yet conversations still sounded robotic. Something fundamental was missing. Nobody realized that the breakthrough wouldn't come from teaching computers more grammar. Instead, it would come from teaching them to predict. That single idea would eventually lead to ChatGPT, Gemini, Claude, and the external language models transforming our world today. But before we reach that chapter, we must first understand the revolution that made it possible: machine learning. Because everything you have seen so far, the smartphones that recognize your face, recommendation systems that know what you will watch next, medical AI detecting disease, self-driving vehicles, and modern conversational assistants all trace their origins to one extraordinary idea. Instead of programming intelligence, teach machines how to learn. And once machine began learning, everything changed. That is exactly where our journey continues in the next chapter. Here we will explore machine learning from Here we will explore machine learning from the ground up, how machines learn, why data is their fuel, and how simple mathematical ideas evolved into systems that can outperform humans at many specialized tasks. The explanation will remain cinematic, story driven, and entirely in paragraph. Imagine that you are standing in front of two children. The first child has never seen a bicycle before. The second child has never seen one either. To the first child, you hand a thick instruction manual explaining every single component of a bicycle. You describe the wheels, the chain, the pedals, brakes, handlebars, gears, frame, balance, friction, and physics involved in riding it. To the second child, you simply say watch. The child watches someone ride, then they try, they fail, they fall, they try again, they wobble, they lose balance, scrape their knees, stand up again. Slowly, their movements become smoother. After enough practice, they ride confidently without thinking about every movement. Now ask yourself a simple question: which child learned faster? The answer reveals one of the greatest secrets of intelligence. Experience often teaches better than instructions. For decades, computers were like the first child. Every task required detailed instructions. Every possibility had to be anticipated. Every rule had to be written by a programmer. If a bank wanted software to detect fraudulent transactions, programmers had to define hundreds or even thousands of rules. If the transaction exceeds a certain amount, flag it. If it happens in another country, investigate it. If the customer suddenly buys expensive jewelry after years of small purchases, raise an alert. But criminals are clever. The moment one rule is discovered, they change their behavior. Soon another rule is needed, then another. Eventually, the number of rules become impossible to manage. The software grows larger, slower, more complicated, yet it still misses fraud. This approach had reached its limits. Scientists realized something important. Humans rarely learn through fixed rules. We learn by observing patterns. Imagine you meet a person for the first time. Within seconds, your brain estimates their age, mood, confidence, energy, and perhaps even their profession. Nobody taught you an exact mathematical formula for doing this. Your brain learned from out thousands of previous experiences. That observation changed the future of computer science. Instead of programming every possible rule, what if computers could learn from experience too? That single question gave birth to machine learning. Machine learning is one of the phrases that sounds incredibly complicated, but the idea behind it is surprisingly simple. Instead of writing instructions for a computer, we provide examples. The computer studies those examples, finds hidden patterns, builds its own mathematical model, then uses that model to make predictions about the things it has never seen before. Imagine showing a child 10,000 pictures. Some contain cats, dogs. Each picture has a label: cat, dog, nothing more. Eventually, the child begins recognizing cats without needing labels. The same process begins inside machine learning. The computer isn't told what whiskers are. It isn't told what ears look like. It isn't taught tails, paws, or fur individually. Instead, it discovers those patterns automatically. This may sound almost magical, but underneath the magic lies mathematics. Lots of mathematics. Suppose you wanted to predict house prices. You collect information about thousands of houses, their size, location, number of bedrooms, age, whether they have a garden, near school, or public transport is nearby. Each house also includes one more piece of information, its selling price. Now imagine placing all this information into a machine learning system. Initially, the computer has absolutely no idea how houses are valued. It, its first predictions are terrible. A small apartment might be predicted to cost 10 crore. A luxury villa might be predicted at 20 lakh. Clearly, something is wrong. But here's the fascinating part. After each prediction, the computer compares its answers with reality. How long was it? Too high? Low? By how much? It then adjusts itself slightly, then predicts again, thousands, millions, sometimes billions of tiny improvements later. Its predictions become astonishingly accurate. This process is called training. Training isn't downloading knowledge, training is gradual improvement. Imagine learning cricket. The first time you bat, you miss almost every ball. Over weeks of practice, your timing improves, your footwork improves, judgment improves. Eventually, you stop consciously calculating every moment. Experience becomes instinct. Machine learning develops in a similar way. Every mistake teaches the system something new. The more quality experience it receives, the better it becomes. Scientists often compare this to climbing a mountain. Imagine landing in dense fog somewhere on a mountain. You cannot see the peak. You don't know the best path. All you can do is take one careful step downhill until the ground stops descending. Eventually, you will reach the lowest point. Machine learning follows a similar strategy. Every mistake tells the algorithm which direction leads to improvement. Step by step, it moves towards better performance. This optimization process is one of the most important ideas in all of artificial intelligence. But here's something even equally important. Machine learning is only as good as the data it learns from. Imagine trying to teach a child about elephants using only pictures of mice. No matter how intelligent the child is, they will develop a completely incorrect understanding. The same thing happens with AI. Poor data creates poor intelligence. High quality data creates better intelligence. The idea become famous among AI researchers. Garbage in, garbage out. The intelligence of a system depends heavily on the quality of its experience. Now imagine another challenge. Suppose you show a machine learning algorithm 1 million photograms. Every single image contains a dog. Not one cat, horse, bird, or only dogs. Then you ask it to identify a tiger. It has absolutely no reference point. Learning requires diversity. Human experience can incredibly rich world. Humans experience an incredibly rich world. Different cultures, languages, weather, emotions, foods, faces. These countless experiences allow us to adapt to unfamiliar situations. AI also requires diverse experiences if it hopes to perform well in the real world. Now let's explore the three major ways machines learn. The first is called supervised learning. Imagine a classroom, teacher asks a question, student answers, teacher immediately says correct, that's incorrect. With every incorrection, the student improves. This is supervised learning. Every example already includes the correct answer. Email spam, not spam, picture, cat, dog, medical scan, healthy deceased. The model learns from labeled examples. Much of today's commercial AI relies on supervised learning because labeled data provides a clear learning signal. The second approach is called unsupervised learning. Now imagine entering a library where none of the books have titles, no labels, categories, instructions. Your task is simply to organize them. Eventually, you notice patterns. These books discuss history, discuss science. These are novels, are biographies. Nobody told you the correct of group. You discover them yourself. This is unsupervised learning. The computer searches for hidden structures that humans may not even realize exist. Banks use this to detect unusual behavior, financial behavior. Scientists use it to discover patterns inside enormous biological datasets. Businesses use it to understand customer behavior. Sometimes the algorithm discovers relationships that supervise even experts. The third approach may be the most fascinating of all. It's called reinforcement learning. Imagine teaching a puppy whether it obeys a command, you reward it. Whenever it misbehaves, no reward. Over time, the puppy naturally repeats behaviors that produce positive outcomes. Now replace the puppy with a robot or a self-driven car, AI playing chess. Instead of receiving instructions, it receives rewards. Every good decision earns points. Poor decision loses points. Eventually, the system discovers strategies entirely on its own. One of the most famous examples happened in 2016. AI system defeated one of the world's greatest Go players. Go is an ancient board game with more possible positions than there are atoms in the observable universe. For decades, experts believed computers would struggle with Go because intuition plays such an important role. Yet the AI didn't simply memorize games, it played millions of matches against itself, winning, losing, learning, improving again and again. Eventually, it developed strategies that even human grandmasters had never imagined. Some professional players described certain AI moves as strangely beautiful, not because they copied humans, because they invented something new. That moment shocked the world. Machines weren't just following instructions anymore, they were discovering knowledge. This marked a turning point in artificial intelligence. People began asking a much deeper question. If AI can discover better chess strategies, better medical diagnosis, engineering designs, what else might it discover? Drug treatments, new materials, fusion reactor designs, climate solutions. The possibilities suddenly expand far beyond automation. AI became a tool for invention, but success also created new challenges. Sometimes machine learning performs brilliantly during training, then completely fails in reality. Imagine teaching someone to drive using only empty roads. The first busy city they encounter becomes overwhelming. Similarly, AI trained on limited situations often struggles with unexpected conditions. Researchers call this overfitting. The system memorizes training examples instead of learning general principles. Imagine a student who memorizes answers without understanding concepts. The moment the exam changes slightly, everything falls apart. True intelligence requires generalization, learning principles, not memorizing examples. Human beings excel at this. A child who has seen only a few dogs can recognize a completely new breed. That ability to generalize remains one of the humanity's greatest strengths. AI continues improving, but general intelligence remains one of its biggest challenges. As machine learning evolved, larger models. Researchers built larger models, more data, computing power, connections. Again and again, performance improved. Then something unexpected happened. Scientists noticed a remarkable pattern. When they doubled the amount of data, performance improved. When they doubled computing power, performance improved. When they doubled the size of neural networks, performance improved again. Instead of reaching a limit, AI kept getting better. This observation transformed the industry. Companies began investing billions of dollars into larger computers, larger datasets, and larger neural networks. The results exceeded almost everyone's expectations. Speech recognition reached human level accuracy in many situations. Image recognition surpassed human performance on certain benchmark tests. Language translation improved dramatically. Medical diagnosis became more accurate. Recommendation systems became uncannily personalized. Search engines became smarter. Digital assistants became more useful. Every industry began discovering new applications. But perhaps the most extraordinary breakthrough was still ahead. Because until now, AI almost recognized existing information. It identified, predicted, classified, recommended. Then researchers asked a breathtaking question. What if AI could create? What if it could generate stories instead of merely reading them? Compose music instead of analyzing it? Write software instead of debugging it? Design buildings, create paintings, invent recipes, generate videos, hold conversations, teach students, explain science, reason through complex problems. At first, these ambitions sounded almost impossible. Yet, within only a few years, the impossible became reality. The world would soon meet a completely new generation of AI, artificial intelligence, not systems that simply recognize patterns, but systems capable of creating entirely new things, new ideas. The age of generative AI was about to begin, and at the heart of that revolution stood one invention that would redefine everything we thought computers could do: the transformer, a, a breakthrough so important that it reshaped the future of artificial intelligence almost overnight. If you enjoyed this journey, don't forget to subscribe and turn on notifications because we are just getting started. The future isn't waiting, it's being built right now, and perhaps you will be one of the people who helps build it. Thank you for watching. I'll see you in the next documentary.